So let us continue our discussion on class field theory over Q. Previously, we have fixed an abelian extension L of Q, and then we described the Galois group of L over Q in terms of the arithmetic of Q. And the way we do it is via Kronecker-Weber theorem. By Kronecker-Weber, we know that L must lie inside some cyclotomic extension of Q. If L, say, lie in the M cyclotomic field, then we can describe the Galois group of L over Q in terms of the group of fractional ideals of Q in the following way. Recall that the group of fractional ideals of Q is just the free multiplicative abelian group generated by the primes of Z. In other words, it's just the unit group of Q. Now inside that, we can look at this subgroup generated by the primes that do not divide M. We have a natural map from this subgroup to the Galois group of the cyclotomic field. Its kernel consists of quotient of integers AB such that A is congruent to B modulo M. Thus this gives an isomorphism between Z mod MZ star and the Galois group of the cyclotomic field. This quotient Cm here could be viewed as a generalization of both the Z mod MZ star group and also the ideal class group. Now, if we compose that map with the surjection from this Galois group, right, to the Galois group of L over Q, then we get a map from this generalized ideal class group here into the Galois group of L over Q. We call this the Artin map and denote it by this. Then trivially, if we denote the kernel of this map by H, then we have an isomorphism between the quotient of Cm by H and the Galois group of L over Q. Now, so far everything just seems like a wordplay. It just seems like we are creating new terminologies without actually introducing any new insight. So now let's see the usefulness of this viewpoint. We're gonna talk about decomposition of primes. It turns out that the kernel of this Artin map will contain all of the primes that split completely in L. Well, not exactly, but at least those that do not divide M. For primes P not dividing M, P splits completely in L if and only if P lie in this kernel of the Artin map. And this is because the order of P in this quotient is exactly equal to the inertia degree of P. Let us quickly recall the definition of the inertia degree. In our case here, because we assume that P doesn't divide N, P is gonna factor in OL into a product of distinct prime ideals. Then OL quotient out by any of these prime ideal is gonna be a finite extension of Fp. And since L over K is Galois, all of these quotients are gonna have the same dimension as Fp vector spaces. We call this dimension the inertia degree of P. Well, technically it's the inertia degree of beta over P, but because it's all the same, so we'll just call it the inertia degree of P. Now it turns out that F multiplied with R, the number of primes here, is equal to the degree of this extension. So P splits completely, i.e. the number of primes here is equal to N if and only if F is equal to 1. Now coming back, since the order of P in this quotient is equal to this inertia degree, we see that P splits completely if and only if this inertia degree is 1, i.e. if and only if P lies inside this kernel of the Artin map. So up next, let us use this idea to prove quadratic reciprocity.